Okay, welcome to the Chapter 7 analysis video. And what I'm going to do for this one, and I think for many of them, is to have everything just on a Word format so that I'm just scrolling down and showing you how I did the analyses. So for the first part of this video, I'm going to do the Jamovi ESCI for the confidence interval on the difference on pages 177 and 178. And that section, the analysis for that section, was based on the study that you see in front of you here by Latimer and others. And the title was, Does Pre-Testing Promote Better Retention Than Post-Testing? So I'm going to go through and read that abstract for you so you can see what the context is. Compared with other learning strategies, retrieval practice seems to promote superior long-term retention. This has been found mostly in conditions where learners take tests after being exposed to learning content. However, a pre-testing effect has also been demonstrated with promising results. This raises the question: for a given amount of time dedicated to retrieval practice, whether learners should be tested before or after an initial exposure to learning content. Our experiment directly compares the benefits of post-testing and pre-testing relative to an extended reading condition on a retention test 7 days later. Okay, so I'm going to stop right there for a second so that you can try to digest that a little bit. And so what we're looking at here is you have to ask yourself the question, what is the dependent variable here? The answer would be right here. It's the retention test 7 days later. This is what's being measured based on certain exposures. And so we have pre-testing right here, post-testing, and extended reading. And so what it looks like they're doing here is they have this extended reading condition, I believe in this context would be like a control condition. And then compared to that reading condition, they're looking at the effects of pre-testing only or post-testing only compared to the extended reading condition as a control on retention 7 days later as the dependent variable. So I think that's pretty much what we have for the setup here. So I'll continue. We replicated both post-testing with a D of 0.74 and pre-testing effects with a D of 0.35. I have that underlined. The reason why I have it underlined is because the database that the book has you call up in order to run some analyses, it looks like the analysis is the results that you find, you end up with a D of about 0.35. So it looks like we're looking at the pre-testing effects for this little section that we're going to go through. So they replicated both the pre-testing and post-testing effects with significantly better retention in the former condition. So of the two conditions, post-testing versus pre-testing, it looks like the post-testing was better. And you can see here we've got an effect size of 0.74 versus 0.35, so it's a little more than the post-testing effect. The magnitude of the post-testing effect is a little more than double what it is for the pre-testing. So it says post-testing also promoted knowledge transfer to previously untested questions, whereas pre-testing did not. So our results suggest that it may be more fruitful to test students after than before exposure to learning content. So there's the abstract for that. And now we can do the little parts in the book to get the results from the data. So the first thing you do is you go to Jamovi and load this Latimer reread quiz file. So that's the name of the file that you're going to load into Jamovi in order to do the analyses. So once you open up Jamovi, you go to the upper left-hand corner of the program where you see the three horizontal lines. Click on that and then hit go to open file and scroll down and see the Latimer reread quiz file. Click on that. You open that up, and then I'm giving you right here, this little picture right here is a little snippet from the file that you just loaded. So we have three variables that show up. We have group, test, and time, test percent and time. And I took a specific snippet of the data so you can see over here in this first variable here on the left that the two groups. Again, there were three in the original study, but it looks like this file contains only two groups. One of the groups is the reread group that you see right there, and then the other group is the quiz group. And in this case, it looks like it's the pre-test quiz. So that's the first variable. The other thing you can see from here is if you look down where the reread group goes to, it stops at number 95. And sure enough, they have equal groups, so there's 95 in each of these two groups. So we have what's called a grouping variable here, and that would be at what level of data. Think about that. This is a variable that's simply naming the two groups so that the computer can distinguish the data from the two. So this is nominal level right here. This would be a nominal level data. And I think that if you look at that little symbol right over here, the little two circles there, so that's a nominal level data or nominal level variable. And then the second variable here is either at the interval or ratio level because it has a little picture of the ruler there. So we have test percent. So on the retention test that was done 7 days later, this is the percent that the person scored on that. And then the time, we're not going to look at time, but time shows up as something you can analyze between the two groups. And the total time, I think, was the amount of time that each person in the study dedicated to all of their learning activities. So this is what that data file looks like, or a piece of it anyway. We have 95 in each group because they had equal groups. So you open the file. Next thing you do then is you go and analyze that. So we're going to go to Analyses, ESCI, Means and Medians, two groups. And then you choose the grouping variable and then the test percent as the dependent variable. And I show you a picture of that over here. So if you look at the picture, as before, you have this box over here on the left with the variables in it, and you just select the variables over. So the grouping variable goes down here on the bottom. So I put group down there, and then your outcome or dependent variable that you want to look at goes in this box up here. And of course, once you do that, then the analysis shows up on the right-hand side of the screen, just like we did before. So one other thing to note is then you can see down here some analysis options. So we have assume equal variances down here. This box is checked. We'll talk about that in a second. This is where we're assuming that roughly the standard deviations are roughly equal between the two groups that are being analyzed. The test percent scores for the quiz group and the test percent scores for the reread group, we're assuming that their standard deviations are roughly about the same for this analysis. So that's what your setup will look like. And then we have the output, which again, I've just kind of copied and pasted the entire output into this Word file so we can take a look at them. So there's the first table that shows up, the overview table. We have the outcome variable, which is test percent. Again, your book is calling it the output variable. I would call it the dependent variable, both the same thing, just a different term there. It's what's being assessed here, and that's the test percent. Then you have your group here. So there's the quiz group, in this case the pre-quiz, and then the reread group as sort of a control. And there's the mean for each of the two groups. And then the next two here, there's our confidence interval for the mean of each of those two groups. So we have, for the quiz, we have a point estimate of 42.8. The lower limit for the confidence is 39.3 with an upper limit of 46.2. And then down below, our point estimate in the population for the reread was 37.3, and there's the lower limit, 33.8, and the upper limit at 40.7. There's the median of the two groups right here, median, and we have interval or ratio level continuous data. And so we're probably most likely going to want to analyze this and really look at the means rather than the median. And the reason why that is that the mean and its confidence interval is a better estimate of the population parameter, usually in this case. The other thing you can look at here, although you would want to actually look at the frequency distributions of each of these groups, but if you remember from last semester, if you look at the median compared to the mean, there's the mean, there's the median. Those two are almost identical. That gives us an indication of whether or not the data are left or right skewed. Okay? In this case, they're almost identical. And so without looking at it's sort of a quick check to see if there's skewness in the data. In this case, there would not be. Okay, if it was positively skewed, the mean would get pulled in the direction of the skew, so the mean would be greater. So if we had a mean like 46 or 45 right here with a median of 42, I would want to look at the frequency distribution, and it would probably turn out that the data would be skewed positively, meaning right skewed. But they're equal here, so we have no problem. And then if you look down here, you can see 37.3 and 33.3. Now this one, here you go. So this one, we have a little bit of a right skew on this data. And if you're actually doing this study, you'd want to maybe look at that to see if you might want to transform it to try to make it a little more normal. But for now, we'll just leave it as is. So the median here, in our case, it's not that useful, but it does give you a quick check on potential skewness. Here's your standard deviation. We have 18.6 and 15.3. They're not identical, but according to the book, they're close enough so that we can assume equal variances. The book says, not in this chapter, it might, but definitely in a later chapter, saying that as long as the larger mean is not twice the size of the smaller, as long as the larger standard deviation is not twice the size of the smaller standard deviation, or approaching twice the size, then you can typically assume equal variances. And so this is close enough for us. This is the standard deviation, and remember the standard deviation, the variance is the standard deviation squared. So again, terminology here, they always say, equal variances, but you could kind of say equal standard deviation, sort of saying the same thing. So we feel pretty comfortable with our assumption of equal variances, because the larger standard deviation is not even close to approaching double the size of the smaller standard deviation. We have n and 95 in each, so supposedly if it's a random sample, we have a pretty good sample size there. No missing values, and our what's called the SP. This is the pooled standard deviation, which is roughly the average between the two standard deviations of the groups. So if you take the average of this here, you're roughly about at 17. This is what's called the SP, or standard deviation pooled. And so in calculating some of the other results, if you assume equal variances, then you're going to use the pooled standard deviation as one of your standardizers. Okay, so there's that first table. Let's take a look at the second table there. So focus your attention right here on the second table. And this is where we look at more of the mean difference situation. So everything else is the same. The only real difference with this table here is this last column right here, last row right here that I'm pointing to at the bottom down here. Everything else is roughly the same, although it looks like compared to the previous table, the means are a little bit different, but we won't worry about that. Confidence intervals are the same as above. So here's our difference. So the difference between 42.7 minus 37.2 right here is 5.4. So that's our quiz score minus our reread mean. So we took the large one and subtracted the smaller one from it. We get 5.4, and there's the confidence interval for the difference. The confidence interval for the difference between the two means. Okay? So as noted before, again, the variances are assumed equal, or i.e. the standard deviations are assumed equal. So the pooled standard deviation was used to calculate the confidence intervals here, the 95% confidence intervals. So take a quick look at these confidence intervals here just to refresh. There's several ways to interpret these confidence intervals. I'll give you 3 of them, of the most common. The first one is that these intervals are one from the dance, if you remember from last semester. And what that means is that in simulations, if you generate random samples from a population and compute confidence intervals, 95% of them will capture the population parameter, and 5% of them will not. And so, for example, with this first one here that I'm pointing to in the first row, you can therefore, for this one, be 95% confident that our population estimate of 42.7 with a lower limit of 39.3 and an upper limit of 46.2 is one of those 95% that capture the population parameter. So we're 95% confident that the true population mean is somewhere between these two numbers, with our best guess as to what that population parameter is is 42.7. And remember, 42.7, you can bring that over here. It'll fit right in the center here, typically, right there, between the lower limit and the upper limit. So that's the first way you can interpret the confidence interval. It's probably the most common. The second way is one of the ways that the book is recommending is to picture it as a cat's eye picture, so that what you can see is that the 39.3 to the 46.2 for this particular interval is the range of probable values for the population parameter. And values that are outside those two limits are possible, but not very probable. The book uses plausible instead of probable, but I'm using that a little bit interchangeably. Okay. The other thing with this particular interpretation about the cat's eye and the probability interval, or the plausibility curve associated with a confidence interval, is that the point estimate is our best guess, and that the probability or plausibility is not the same throughout the range from the lower limit to the upper limit. The plausibility or probability is highest in the center where our point estimate is, and it decreases as we go to each of the limits. And then the third way is to interpret it as a prediction interval for a replication study. If you remember, the book talks about that. So it would be considered a 83% prediction interval. So if someone else did a study and tried to replicate this one, the Latimer study, and they tried to do everything exactly the same, there's about an 83% chance that the mean that they would obtain for their pre-test quiz group would fall within this interval that we have here. So we're roughly 83% confident that if someone tries to replicate it, the mean that they obtain will fall within the interval that we have here, this 95% confidence interval. So those are the three ways you can kind of think about these confidence intervals, with the first two being the most common as far as just describing what you have at hand. I want to move down now to this picture here, which relates to the second interpretation that I was focusing on as far as confidence intervals. Get that in there. Okay. And that is that you have this plausibility curve, right? And so what your book author did was develop this curve by looking at the frequency with which the mean of a confidence interval comes close to the population parameter versus the frequency with which either a lower limit or an upper limit comes close to the population parameter in a random simulation study. So for example, this first arrow up here, this first orange arrow, we have a case where the mean for that confidence interval, if you look right there, the mean for that confidence interval, the green circle, is just a little tiny bit below the population parameter of 50 down here. Okay? Here's another case. The second arrow here is virtually the same thing. We have the mean of the confidence interval from the particular sample That mean is just on the other side. It's very close to the population parameter. Okay, so that's what I mean by the frequency with which these types of cases where the mean is very close to the parameter versus the cases in these next two arrows here where a lower or upper limit is close to the population parameter. So you remember, the reason I have this up here is so that you can kind of refresh your memory about that dances of the mean thing. And in so doing, you can develop this plausibility curve or probability curve associated with a 95% confidence interval. And the way that's done is to plot these error differences, the differences between the mean and the parameter or the upper or lower limit versus the parameter. So here's a first example of the other kind of case. What about this confidence interval right here? Here we have a case, if you look right here, the lower limit here, right over here, is very close to the population parameter. So here the lower limit is just below the parameter. Right there, that distance there. There's the lower limit, there's the parameter. Okay? That's a case where we have the lower limit close to the parameter. And then if you look down here, this is a case where the upper limit is just above the population parameter. So that's where that plausibility curve is coming from in terms of your mind's eye when you look at a confidence interval. And the point of the matter is it's why we think that our mean is the best bet for the estimate of the parameter. So if you run this, you keep running this, the frequency with which these kind of cases occur in the first two arrows here, a case like this or a case like this, the frequency with which these two cases occur, these types of cases, versus the bottom two types of cases, is about a 6-to-1 ratio, roughly, or about a 20-to-3. So for every 20 times that we get a case like this or this, we only get about 3 of these kind. Okay? And so from there, you have your plausibility curves. You can go back in the book and check on that. And he's just trying to give you a visual picture that the probability of any value in the range of the confidence interval is not equal as far as its accuracy or estimate of the population parameter. So we feel that the mean inside that interval is about a 6 times better bet to be a good estimate of the population parameter than any of the values that are close to either the upper or lower limit. Okay. So then here's our standardized difference. You've seen a table like this before. It's the same output from the Latimer study. So if we look at, go from left to right, there's our test percent. There's our quiz minus reread. And there's our mean difference that we saw before, the 5.46. And there's our pooled standard deviation, which is 17, which in this case, because the sample sizes are equal, it's roughly the average between the two. There's a formula in the book for that. It's the pooled standard deviation. Essentially, it's a sample size weighted average of the two standard deviations that you're looking at. Okay, And then to get the effect size, you just take the 5.46 and divide it by the 17, and you get this value right here, 0.32. Okay, that's our D effect size. That's how many standard deviations in the population, how many standard deviations the quiz group is above the reread group on the retention test. About a third of a standard deviation, which would be a kind of a somewhere between a small to a moderate effect, I believe. So it's detectable, it's there, and an effect of that magnitude does have some importance in the real world, meaning that it's worth your time to do the quizzes, either pre or post, post being better, but we're looking at the pre, um, to help students retain the information. There's the confidence interval for the D. So this is the D. There's the confidence interval for that. And it sort of apply the same thing that I talked about before with the confidence intervals apply here for the most part. We have the lower limit is pretty close to zero there on that one, 0.0327, with an upper limit of about 0.6. Okay, with our 0.32 sitting right in the center there. And then he also includes the biased here. And so you sometimes you can look at this this D biased versus the D that they're showing here. And he's calling it DS because he's using the pooled standard deviation for the standardizer, which is a very important consideration in these D values, is what's the standardizer used, because that can make a difference. In this case, if you look at the difference between the corrected one for bias versus the uncorrected one, there's essentially little difference. They're both 0.32. And the reason he's putting that there again is because it's been shown mathematically and through simulations that the D statistic, which is the standardized difference between two means, in our case, our effect size, is a biased estimator of the population parameter that it's trying to estimate. It becomes not as good as the sample sizes get small. Okay, as the sample sizes get small. Okay, and so what it does is the sample sizes get down around 20, 15, 10, 8. Then when you calculate the D from a small sample, the D that you get is larger than the actual population parameter. So if you set the population parameter, if you can do this on a computer, you already know what that parameter is, and then you take samples and calculate D's. As the samples get small, the D that's calculated from the sample overestimates the parameter. That's not good. That's bad. What we want is the most accurate one we can possibly have. So D is good, but it becomes biased when the samples get small. And so they've come up with a correction factor for it as the samples get small. And in this case, since the sample is 95 or higher, in this case, there's very little correction because the sample is pretty big. So if you note down here, this standardized mean difference is called DS because the standardizer was the pooled standard deviation. DS has been corrected for bias. Correction for bias can be important when the degrees of freedom, i.e. basically the sample size, is less than about 50, okay? And the rightmost column has the biased value. So, yeah, less than 50, even at 50, the correction is the bias is pretty minimal. It's when you get down around 20 and 15 and 10, then you need to really, you're gonna see a noticeable difference between the biased and the unbiased. So your book, if you're reading through the book a little bit, he's advocating, always using the unbiased version. Okay. And there's just a little formula that's applied to the biased one over here. There's a little formula that's applied to it that'll correct it to give you the unbiased. Okay, another little quick thing here too about the terminology. So if you remember from the first table up there, we had an N of 95 in each group. And the N that was used was a small n, small. Whereas here you're saying if N is, big N is less than 50. And so the small n is for each group size. Big N is for the entire sample, the entire study. So we have a small n of 95 for each, right? And so our big N is 190, I believe, right? 95 and 95 would be 180 plus 10, and that would be 190. So that's why you're seeing basically virtually the same thing. There's very little correction needed there. Here's our estimation figure you can take a quick look at. Again, this is the only program that I've ever seen that uses figures like this, which are very helpful, I think. It's just another way of kind of looking at the difference. So on our y-axis here, we have our dependent variable. And as a rule of thumb, the outcome variable or the dependent variable almost always goes on the y-axis for your plots. And then the independent variable, in this case, it's sort of categorical. We have the reread group and the quiz group and the difference. Those kinds of things go on the x-axis. So this is a nice little figure you can see. Here supposedly is the reread data, kind of put out in sort of a dot plot with its mean and associated confidence interval here and its plausibility, little plausibility curve there, okay? And then you go over, okay? And that again, that's like the control group. So that's being set at 0 for the difference, right? And then the quiz group is in the green, and there's your quiz group here, okay, as a dot plot. So supposedly, if the computer is doing it, we would have how many dots would we have here and how many dots would we have here? Supposedly we would have 95 here and 95 there. I don't really feel like counting them right now, but that would be kind of the idea that you'd have, right? And so you can trace this back to what you have here. So there's the mean for the quiz and its confidence interval and its 90 and its sort of probability or plausibility curve, right? So we have our what over here is our 37, etc., and our 5 about 5.6 or something difference. And so we show the difference right here. Okay, so you can see the triangle is showing the difference with its 95% confidence interval there using the pooled standard deviation to calculate the confidence interval. And so we can see this confidence interval, 0 is not really a plausible or probable scenario. So we're feeling pretty good about that, right? And we could go as high as about 10 percentage points differences between those two. So this gives us a nice little estimation figure with the confidence intervals and plausibility curves, or probability curves, if you will. Okay, so that takes care of that section. Let's move on to the next one that I'm going to do here, and that's interpreting D in context and the probability of superiority using the ESCI web, and that's on page 193 to 195. And this goes fairly quickly here, you can see. So when you evaluate D, remember D is an effect size for the difference between two means. Okay, so it's the difference between the two means in standard deviation units or standardized units, making it good so that way you can compare different studies on a standard scale. So some of the things you should consider would be the standardizer that you choose. Because remember, D is a ratio. The numerator is the difference between the two means. The denominator is the standardizer, is what he calls it. And so different standardizers are available, and the choice of which depends on the context and the data that you have and lots of things. The point is, though, you want to make sure you tell people which standardizer you're using. Big faux pas if you don't do that. The other thing you can do then is you can look at the D overlap picture, which you can see in the ESCI web, which I'm going to show you some pictures of that in a couple seconds. Okay, the D overlap picture is good because it can give you this thing called the probability of superiority, which is just another sort of like a supplement. Not necessarily in my mind a substitute, but a supplement to the actual D value and its interpretation. And then the last thing you can consider are values that are typical to your discipline if you want to use certain kind of benchmark values. So for example, again, we're kind of trying to consider it in context here. So 0.2, 0.5, 0.8 for small, medium, and large. That's Jacob Cohen for the discipline of psychology, or 246, 0.2, 0.4, 0.6, small, medium, and large for Hattie for the, I think that's how you pronounce it, for the discipline of education. But remember, those are just guidelines here, so. Let's take a look at that overlap picture. So this is figure 7.7 from the textbook right here. I'm showing two of them. One is a D value between two groups. Now you can see the little curves there, the frequency distributions for each group. There's two curves, a blue curve and like a red or pink kind of curve. And the frequency, again, the y-axis is being cut off here. The frequency is over here on the y-axis, but they're not showing that. And then the actual D value or the standard deviation units here are on the x-axis. So the first one we have a D of 0.57, showing that the curve or the group represented by the red distribution, which is right there, the red distribution with its mean is right there, being a little more than a half a standard deviation shifted to the right or greater than maybe the blue. That might be the control, for example. The other thing you're seeing in this picture, which I've added, is the amount of area for the red distribution that's above the mean for the blue distribution. And that's about 72%. That's I took a little pencil and drew a pink line with slash marks through it so you can see that there. Okay. That gives us the D of 0.57. Just real quick, the 0.72 that you're seeing here, that's the amount of area for the red distribution, or maybe like the experimental group, that's above the mean of the control group. It's not the probability of superiority, which I'm going to explain in a second here. It's not that. It's kind of like that, but it's not really. So keep that in mind. And then you see this picture over here on the right-hand side. It's the same thing, only there's just a tiny little shift to the right for the red. Just barely. You get this D of 0.04, which is essentially meaningless. Okay. You can see also then if the groups don't, if there's no shifting of the groups and they overlap completely, then what you have over here would be 50%, right? It's 50%, and then as the one group shifts to the right or left or what have you, then you get a larger percentage of one group above the mean of the other. So that's figure 7.7. So now we can now you can use the ESCI web and try to calculate, or it'll calculate for you, the probability of superiority. So let's do that, and I did that. So I went up to the ESCI web, went to dpicture, and I kind of replicated this figure 7.7. So let's take a look there. Bring it up a little more. There we go. So there's the ESCI web, the dpicture. Okay, and this is pretty simple. It's just two means. You have two groups, and all you do is you go over here to the right panel, and you use this little slider over here to set the D value that you want. Okay, so again, up here we had 0.57, so I just went down over here when I was up on the internet, and I just pushed this over, and then you can use these little buttons here to make it go like a tenth, to kind of fine tune it a little bit. So I have 0.57, and so now the picture I see here is the same as the figure 7.7. We have a D of 0.57 with 72% of the area of the red curve above the mean of the blue curve. Okay. So experimental, for example, was red, control was the blue, if you will. And then what you can do is you can come over here and hit these little tick boxes over here to get your little areas, but it also automatically computes what's called the probability of superiority. And so what is that? It's actually pretty simple. It's the following. It's the probability, if you were to randomly select a person from the experimental group and randomly select a person in it. So if you look at the figure here and randomly select a person from the control group, it's the probability that the person from the experimental group will have a higher score than the person that you selected from the control group. So in this case, it's about 66% chance. So what that means is there's about six to seven times, not quite seven, but somewhere between 6 and 7 times out of 10. If you randomly picked one person from each group, okay, let's say you did that 10 times, on average, somewhere between about 6 and 7 times out of 10, the person that you selected from the experimental group would have a higher score than the person that you selected from the control group. That's it. That's the entire situation there. Okay, or if you did it 100 times, right? If you did this 100 times, you did a little simulation. So you picked one person randomly from the experimental, picked one person from the control, put it in the computer, picked one person from the experimental, picked one person from the control, put it in the computer. If you did that 100 times, roughly about 65 to 70 of those individual comparisons would be a case where the person that you selected from the experimental group has a higher score than the person you selected from the control group. Okay, so that's what's called the probability of superiority. It's sort of a supplement to the d-value effect size. And here's the same thing for that other d of 0.04. The 0.04 is really useless because there's nothing there, right? I shaded it. The probability of superiority, it's a flip of a coin, which means that one group isn't really, there is no superiority. There's not one group that's going to be higher. So if you randomly select one person from each group, it's pretty likely that they're both going to have basically the same score. Okay, so that's that for that one. Oh, and there's the definition of it right there. So the probability of superiority is a way to estimate an effect size for comparing two samples. The PS is the probability that a randomly selected score from one group exceeds a randomly selected score from another group. So, this is basically something you can sort of just add to your results. Okay, because when you present results to people, you want to present as several different ways so that people can understand it and get a kind of a picture of what it is that you have. This is just another tool that you have to do that. Let's take a look at figure 7.5. This is the last section here. And we're going to look at the probability of superiority for these two things, these two curves. This is again figure 7.5 from the book. This is American women and men height and weight differences. Okay, so the weight is over here on the left and the height is on the right. Okay, so if you look back over to the left, we see a d value for weight between women and men of about 0.81, 0.8 of a standard deviation higher. And so the difference between the two means that on average men are heavier than women with a d value of 0.8, which is a fairly good size effect. Okay, which is a fairly good size effect. We see this little overlap here. Nearly 80% of the men are heavier than the average woman. Okay, nearly 80% of the men are heavier than the average woman. That's what that's showing here with the 79% on the shaded area for the men, with a D of 0.81. Okay, so the effect of being a man is a strong, if you will, effect of potentially being in one category or the other, being either a man or a woman, is a strong effect of potentially how much that person's going to weigh. Okay. And on the height side, if you look over on the right, it's huge. We have a D of 2.26. That means that, wow, that means that it's men are undoubtedly more than two standard deviations in terms of distributions on average taller than women. And this is a very large effect. So 99% of the men in the United States anyway are taller than the average woman. That's what that's showing. 99% of the men are taller than the average woman, average female. Okay, so there's a massive separation there in height. Okay, Okay, so let's find the probability of superiority for each one of those, and I did that. So I went to, we have the D's of 0.81 and 2.26. It's a difference in standard deviation units. Pretty good sized differences, particularly for height. What's the chance that a randomly chosen man is heavier than a randomly chosen woman? So you go up there to the D picture for the ESCI web, move the little slider over till you get D of 0.81, okay, and you're done. And so we have a probability of superiority there of about 72%. So if you just randomly took a man, now I'm not saying anything about age here, but that might be a factor, but we'll just kind of suspend your disbelief for now. So again, randomly select from males and randomly select from females. There's about a 72% chance that the man is going to weigh more than the woman, according to this. Okay, just the interpretation of the what you have. Okay, and then for the height one, I did the same thing, and that one's massive. So here's the 2.26. There's a massive separation between these two. Okay, so in terms of the standard deviation in the population for both of these groups combined, men are more than 2 standard deviations on average taller than females. Okay, with a probability of superiority of 95%. That's pretty large here. Okay, 95% chance. If you just randomly pick, using some kind of a random process of picking a male and a female, the male is going to be taller. So if you're a betting person, you're going to bet that if someone does that randomly, you're going to put your money on the male being taller. Okay, because according to this, there's a 95% chance that you're going to win the bet. And then the very last one is the question is, why are they so different? So let's take a look at that final thing. It's right here. Okay, so if you look at, your friend is surprised that the D values for weight and height are so different. Why is this? Well, basically, because the standard what's happening in this case is this is a reminder that your book author says to you is to always look at the denominator of the D value. Look at that, what's going on with the denominator, because it's a ratio. So in other words, there's more than one thing that can make the D value larger or smaller, right? On the one hand, you could have a large difference between two means that creates a large D value. Or you could have a sort of a relatively small to moderate difference between two means, which is the numerator, but you have a really small standardizer, right? So if you have a really small standardizer, what does that do? It sort of jacks up, right? It makes that ratio bigger. And that's what's happening here. Okay? So the deal with weight is over here, okay, men are about 13 kilograms heavier on average, which is about 28 pounds, somewhere in there, 27 and a half pounds heavier on average than females, right? And the pooled standard deviation that's used for the D is 16 kilograms. So the D is 13 divided by 16.8. Okay. Height. Men are about 14 centimeters taller on average than females. Okay. Or roughly what? Somewhere in the neighborhood of about 6 inches. Something like that. okay? Um, and the pooled standard deviation there is 6 centimeters. So keeping in centimeters, right? Or centimeters. So in this case, we have 14 divided by 6 is 2.3. So this is what I was talking about. You can see that the numerator, men are about 13 kilograms heavier for the numerator, and for height, they're about 14 centimeters taller. So the numerator, just the absolute sort of value or magnitude of the numerators are roughly about the same, but the difference is in the denominator. Here up above, we divided 13 by 16, we get 0.8. Here we divided just one higher, 14, right? 14, but we divided by 6. Now you're getting this massive, you're getting this big, difference there. So this is one thing you got to keep in mind when you look at these effect sizes, is to consider both the numerator and the denominator, so that you really have all the information and you kind of know, what you're looking at. Okay, so ignorance is not bliss on this. You want to make sure you have the information, so that this would be a great example of a question that someone could ask you, like on a dissertation defense or something, you know, where if you hadn't thought about that, you're going to be thrown for a loop. Okay. Again, men, the weight and the height thing, you're like, okay, yeah, I get it. Men on average are heavier than women, and men on average are taller than women. But then you look at the D value effect size, we have a D of 0.81. Okay, that's about right. I would consider that to be, just about right, about 8/10 of a standard deviation, because men are heavier, right? They have more muscle, blah, blah, blah. But you might think that, well, the height one then should be, maybe in the same ballpark as weight, right? Like 0.8, 0.9, 2.26. Like, what is going on here? Okay, so that's what the point of this little section is about. Is it, you wouldn't want to change anything, because this is what it is. It's just that that difference there. Don't let that throw you for a loop. It's everything is sort of copacetic as far as weight and height, but the reason that this 2.26 is so much higher than what you might think it would be is because this denominator down here is smaller. Once you see that, then you're like, oh, okay, I sort of get it now. Okay, so that takes care of that analysis video for chapter 7. That'll be posted up. And then I have, just like last semester, I have for each analysis video, like you just watched right now, there'll be a 5-point quiz for that. So thanks for watching. And if you have any questions about any of it, just send me an email.